Okay, so we continue discussion of tutorial on WKB approximation. So our next question, the second question is using the WKB approximation, find the allowed energies of a particle. Second. So find the allowed energies of a particle in an infinite square potential of the type shown below. So this is the potential diagram which is given. So the potential is there between 0 to A. So from 0 to A by 2, the potential is V0, and from A by 2 to A, the potential is 0, and thereafter at all other point, the potential is infinity. So it is like a potential well, but there is a small hump, a small bump between 0 to A by 2. A square bump is available there. Okay. Now I have to use the WKB approximation to find the possible energy for this particular problem. Okay. So in order to solve this problem, so look at this problem. So it has at x equal to 0 and x equal to a. It has a rigid wall. That is, the particle cannot go beyond x equal to 0 and x equal to a. So two rigid wall is present in this problem. One is at x equal to 0 and other one is at x equal to a. So if the rigid wall is present in a problem, then the quantization condition is given by if you look at in problem 1. Okay, so recall from problem 1, it's integral 0 to a p of x prime or p of x dx equal to n pi h cross. Okay, so here I can divide this integral into two part. Integral 0 to a by 2 p of x dx plus integral a by 2 to a p of x dx gives n pi h cross. Okay, now p of x, the momentum, is given by square root of 2m e minus p of x. Okay, now between 0 to a by 2, the potential is given by v0. So therefore, the momentum between 0 to a by 2, I can write momentum as square root of 2m e minus v0. And whereas from 0 to, a by 2 to a, the potential was 0. And hence, our momentum p of x is simply square root of 2me. Okay, so this is our equation number 1. So hence, my equation number 1 will take the form integral 0 to a by 2 square root of 2m e minus v0 dx plus integral a by 2 to a root of 2me dx gives n pi h cross. Now root 2m e minus v0 is just a constant. I can take this constant outside. So this become root 2m e minus v0 times a by 2. The integral dx from 0 to a by 2 will give a by 2. Because again here root 2m is just a constant. And if you integrate from a by 2 to a, again you will get a by 2. And that would be equal to n pi h cross. Okay, so a better a by 2 is common. You can take a by 2 to the right side. So therefore, the equation will be root of 2m e minus v0 plus root of 2me equal 2n pi h cross divided by A. Now we have to solve this equation to find the energy. Okay, so the solving this equation is not a very difficult part. Just you square it and do the problem, and we can find the energy as well. Okay, so I think that part you can do it yourself. So if you want, I will give the final answer. You can resolve it in your own time. So the final answer will take the form if you do it very carefully. So the energy will be equal to n square pi square h bar square divided by 2m a square plus v0 by 2 plus v0 square divided by 16 times n square pi square h square divided by 2m a square. Now remember this quantity n square pi square h bar square divided by 2m a square is nothing but the energy eigenvalue of free particle in a one-dimensional box. And so this quantity I can write as En. Okay, better I will put a symbol En0. So hence the total energy will take the form En0. This is the energy of particle in a box plus V0 by 2 plus V0 square divided by 16 times En0. Okay, so that is the final result. So this you can do it yourself. Just an exercise for you. Okay, so if you have a small bump inside the particle in a box, there will be correction in energy, and there is a correction factor. So if there is no potential inside that well, that the total energy is simply equal to n0, and there will not be this term. This the second and third term would not be present. Okay. Now here, what would happen is within that potential well, there is a small bump up to a distance to 0 to a by 2, and which is of the height of v0, and this is the correction. Okay, and this correction now we have calculated using WKB approximation. Now I am giving an assignment to you. Okay, the question is find the energy eigenvalue of this problem using the same thing you can calculate using time independent perturbation theory that you already studied. Using time independent perturbation theory. Okay, so in the time independent perturbation theory, the correction in energy, you can calculate the correction energy would be the expectation value of the perturbed part of the Hamiltonian in the unperturbed energy eigenfunction. Okay, so using first order, so no need to go for second order, using first order perturbation theory. So this you have already done, you have found it. Okay, so yeah, the original system can be considered as a particle in a free particle in a box, and so therefore the total Hamiltonian is h0 plus h prime. This h prime is nothing but v0 between 0 to a by 2. So this you can do it yourself, and that is your next assignment on WKB approximation. Okay, and you can compare the result and compare the result. So we already calculated the energy eigenvalue using WKB. Now you can find the same energy using the first order time independent perturbation theory. Okay, now we can move onwards to our next question. So our next question is the question with no rigid walls. Okay, so obtain the condensation condition on energy with no rigid walls, but two classical turning point is present as shown below. So the situation is like this. We have a potential V of x and some slowly varying function is there. So there is no rigid walls present on any side. Okay, but the total energy was this is our total energy E. So hence we have turning points. These turning points we can call it as a classical turning point. So I'll put this point as x1, this point is x2. So x1 and x2 are classical turning point. So I can divide this the entire region into three. The region 1, which is classically not permissible. Region 2, which is classically allowed region. And the region 3 again not permissible. So 1 and 3 classically forbidden region, and the region 2 is classically allowed region. Okay, now we already found how to connect the WKB wave function from 1, 2 and 3, and that can be done using the connection formula. Okay, now what would be our WKB wave function near x2? So near x2, what would be our WKB wave function in region 2? So near x2, the WKB wave function. So better I will use the sine function so that we can refer the previous discussion. So it can be written as c by square root of p of x sine of 1 by h cross integral x to x2 p of x dx plus some arbitrary constant. Okay, now the same region, so for the region just less than x2, we have a patching wave function. Again very close to x2, we can have a patching wave function. So the patching wave function will take Airy function, and for this x less than x2, this Airy function will take the form a by square root of p of x sine of 1 by h cross integral x to x2 p of x dx plus pi by 4. Now by comparing these two, I can identify this c must be equal to a and alpha must be equal to pi by 4. Okay, so in the region 2, so the one form of WKB wave function. Okay, how can we write the WKB wave function? So in region 2, the WKB wave function can be written as some c, some constant by root of p of x, the sine of 1 by h cross integral x2 x2 p of x prime dx prime plus pi by 4. Okay, so this is the we can put it as equation number 1. Now consider our next turning point. The next turning point is x1. So what would happen near x1? So near x1, how can you write the WKB function? Psi 2 WKB of x. We can write some constant by root of p of x, and obviously since it is the classically allowed region, the wave function would be harmonic function. So sine 1 by h cross, and the limit would be from x1 to x. That is only difference, p of x prime plus some constant beta. Okay, again near x1, this is for just x greater than x1, we can consider a patching wave function. So patching wave function. So patchy wave function will take a wave function. Okay, and that we can found as e by square root of p of x sine of 1 by h cross integral x1 to x p of x prime dx prime plus again pi by 4. Now from this we can say that this capital D must be equal to E, and your beta must be equal to pi by 4. So then in region 2 we have another form for the WKB wave function, which is psi 2 WKB of x. We can write some constant by root p of x sine of 1 by h cross integral x1 to x p of x prime dx prime plus pi by 4. So actually both these equations, equation number 2 and equation number 1, must be same. Okay, so that means this quantity and this quantity must be same. Okay, now from that we can find, we can calculate or we can prove the quantization condition for energy. Okay, so better we can start from equation number 2. Okay, so the equation number 2 states the sine of 1 by h cross integral x1 to x p of x prime dx prime plus pi by 4. This must be equal to sine of 1 by h cross integral x to x2 p of x prime dx prime plus pi by 4. Okay, so we have to prove this. So we can start from LHS. So the sine of 1 by h cross integral x1 to x P of x prime dx prime plus pi by 4 can be written as sine of 1 by h cross integral x1 to x2 P of x prime dx prime plus 1 by h cross integral x2 to x P of x prime dx prime plus pi by 4. Okay, so far so good. Now that can be written as sine of 1 by h cross or minus 1 by h cross. Okay, better I'll write plus. So plus 1 by h cross integral x1 to x2 P of x prime dx prime minus 1 by h cross integral. I am just interchanging the limit of the second term. So x2 to x I can write minus x2 P of x prime dx prime minus pi by 4 plus pi by 2. So what I have done is this pi by 4 I have written as, okay, sorry, this pi by 2. This pi by 4, this pi by 4 I have written as minus pi by 4 plus pi by 2. So it's okay. And this plus integral x2 to x I have written as minus integral x to x2. So that is what I have done now. Okay, now the sign of some constant plus pi by 2 can be written as a cos function. Now for our simplicity, what I am going to do is I will denote this entire term as theta. So this can be written as a sine of theta minus this term. I will put it as phi. So sine of, so this term become sine of theta minus phi plus pi by 2. Okay, so sine of theta minus phi plus pi by 2 is nothing but cos. So this become cos theta minus phi. Now the cos function cos A minus B I can write cos theta minus phi can be written as cos theta cos phi plus sine theta sine phi. Now just substitute what is your theta and phi are. So cos of, where theta is 1 by h cross integral. Okay, better don't put theta now. We'll keep the theta there. Cos theta. And what is cos phi? We'll just substitute by your cos phi. So phi is 1 by h cross integral x to x2 p of x prime dx prime plus pi by 4 plus sine theta sine of 1 by h cross integral from x to x2 p of x prime dx prime plus pi by 4. Now according to our this equation, okay, might be question number 3. Now from this equation is very clear that this LHS, okay, now to make the LHS equal to RHS, this term must be 0 and sine theta must be 1. So then only what will you get is would become RHS, because this term is same as your the RHS term. Okay, so in order to get the LHS equal to RHS, the first term must be 0 and in the second term the sine theta must be 1. Okay, so this is valid when cos theta is 0 and sine theta 1. It is a simple condition. So the condition would be, okay, so this is possible if cos theta equal to 0 and sine theta equal 1, and that is possible when theta is multiples of pi by 2. Okay, so then what, how can I write? So this theta must be some n plus half times pi, where n can be 0, 1, 2, etc. Okay, then what is theta? So theta, that we already found, the theta is 1 by h cross integral x1 to x2 p of x prime dx, when that is your theta, and that must be equal to n plus half into pi, or integral x1 to x2 p of x prime dx prime must be equal to n plus half times pi h cross. So now we have got the quantization condition. So this is, I can call it as a quantization condition. Now this quantization condition can be written in terms of energy as well, because p of x or p of x prime is nothing but square root of 2m e minus v of x prime. So therefore the quantization condition can be rewritten as integral x1 to x2 square root of 2m e minus v of x into dx equal n plus half into pi h cross. So pi h cross is nothing but h by 2. So better I will write pi h cross. Okay, so with this we have found the quantization condition for energy. If you have no rigid walls, so this is a condition for no rigid walls, but we have two turning points. Okay, now from this it is very easy to solve the problem of harmonic oscillator. So using this condition, I can find, it is possible to find the energy of a harmonic oscillator. Okay, so that can be my question number 4. So find the energy of a harmonic oscillator using the quantization condition obtained from WKB approximation. So remember the harmonic oscillator, the potential V of x is half m omega square x square. So if you plot the graph, okay, okay. So this is the harmonic oscillator potential. Now if you have energy, the energy we'll put as E. Then we'll have two classical turning points. So if the total energy, if I am writing as half m omega square x0 square is turning point I can put as plus x0 and minus x0. Okay, so according to the quantization condition, what is your quantization condition obtained in the previous section? So in WKB, the integral from one turning point to the other turning point. So this plus x0 and minus x0 are the turning points, because greater than x0, the potential is greater than. So this region has the potential greater than E. So this region also the potential greater than E. And that is not permissible according to classical mechanics. So that is why this plus x0 and minus x0 are called the classical turning point. So in WKB approximation, what we have found is from in the integral x1 to x2, p of x dx is n plus half times pi h cross. So here in the problem of harmonic oscillator, the integration is from minus x0 to plus x0, and the momentum I can write root 2m e minus v of x into dx equal n plus of pi h cross. Now we can do the LHS first. Okay. Now in LHS, I already said E is half m omega square x0 square, and v of x is this. So therefore, this would be square root of 2m can be taken outside. So in the energy, half m omega square is common. So integral from minus x0 to plus x0. Okay, I think better I will do the step. I am not skipping the step, so that will lead to confusion for some of you. So better minus x0 to plus x0 square 2m, and what is your energy? Half m omega square x0 square minus half m omega square x square. So half m omega square is common, dx equal. So it would be the 2 would cancel, 2 would cancel, and root m square omega square. So root m square omega square can be written as m into omega integral minus x0 to plus x0 square root of x0 square minus x square into dx. Now since this integration is an integration of even function, it is possible to write it as 2m omega integral from 0 to x0 square root of x0 square minus x square dx. Okay, so far so good. Okay, now in order to calculate this, better I will use an substitution. I can write some x equal to x0 some sine theta, and hence dx become x0 cos theta d theta, and x equal to 0 implies sine theta equal to 0, and x equal to x0 implies sine theta equal to 1. Okay, so then this integration become 2m omega integral 0, this sine theta equal to 0, sine theta equal to 0, better I put theta equal to 0, and sine theta equal to 1, better I put theta equal to pi by 2. So 0 to pi by 2 root of x0 square minus x0 square sine square theta, and dx is x0 cos theta d theta. So that become 2m omega integral 0 to pi by 2. X0 can be taken outside, so x0 square will get outside. Okay, and cos theta, and the 1 minus sine square theta is again cos theta, so we'll get a cos square theta d theta, and cos square theta is 1 plus cos of 2 theta by 2. So this would be equal to 2m omega x0 square 1 plus cos of 2 theta by 2, and integral d theta from 0 to pi by 2. So here 2 would cancel, and this become m omega x0 square. If you integrate it, we'll get theta plus sine of 2 theta by 2, and the limit is from 0 to pi by 2. And if you put the limit, this sine 2 theta term would cancel, because sine if you put theta equal to pi by 2, that becomes sine pi is 0. If you put 0, again the sine 0 is 0. And if you give the limit for theta, you will get pi by 2 minus 0. So the final answer is simply pi by 2. Okay, and this is equal to the RHS n plus half pi h cross. And what would happen? The pi would cancel. Okay, now we have m omega x0 square by 2, and we know that energy is half m omega square x0 square. So therefore this term is same as energy divided by omega. That would be equal to n plus half times h cross, and this implies that the energy of harmonic oscillator En would take the form n plus half h cross omega. Okay, so we have so remarkably we have got uh, the expression for energy. So it's very simply we have got the expression of energy of harmonic oscillator. So we have in the last chapter, that is in while discussing the formulation of harmonic oscillator quantum mechanics, we have solved the harmonic oscillator problem in detail using wave function formalism and also the operator formalism. And we have got this energy, the energy of harmonic oscillator is n plus half h cross omega, and we have obtained the same energy but using some another way. We have applied the quantization condition from the WKB approximation. So in certain cases this approximation will become very powerful to simplify our problems. Okay, so that's it, our discussion, and I think we can stop it here. And so I will summarize the main conditions of the WKB approximation, the quantization conditions in WKB approximation, and we'll give certain assignments to you so that you can do it yourself. Okay, so I will just summarize the quantization condition in WKB approximation. So if you remember these quantization conditions, we can directly use the result. So the first case, two rigid walls, the system with two rigid walls, that is the rigid walls are the infinitely the potential with infinite height, the walls with infinite height. Okay, so in such problem, so consider, I think better I will draw the graph, then only it would become very easy. and in between the potential may take some form. Okay, so from 0 to a it will have some potential. Okay, so in such cases the condition is integral 0 to a p of x dx is n pi times h cross. Okay, so that is our case 1, and next we can go for case 2. The case 2 is no rigid walls. Okay, but two turning points. So no rigid walls, but two turning points. Okay, so that as we discussed in the last case. X1, X2. Okay, so if you have if there is no rigid wall but there is a two turning point, then the condition would be integral x1 to x2 p of x prime dx prime becomes n plus half times pi h cross. Okay, and there is another case, the case 3, that we have not discussed, but I will give the result. So the case 3 is the potential with only one vertical wall. One vertical wall. So the situation would be like this. Is going up to infinity. Okay, so v of x is infinity for x less than 0. It is some function for x greater than 0. Okay, so there is only one vertical wall present. So okay, so in such cases, if you have only one vertical wall, and obviously there will be some turning point. Turning point will put as some a. Okay, the condition is integral 0 to a p of x prime dx prime equal n minus 1 by 4 times pi h cross. Okay, so that is the third case. So these are the most popular three cases that we will face while solving the problem of WKB approximation. So I will give one assignment based on this case 3 for you. For example, like the potential with the half of harmonic oscillator. Okay, so if the harmonic oscillator is split into two. Okay, so suppose if there is no potential, the potential is infinity for x less than 0, and the potential is present only for x greater than 0. So that is if you split the potential of harmonic oscillator into two, what would be the energy, so that you can calculate from this particular expression. Okay, so I think we can stop it here. Okay, so with this, we have completed discussion of the tutorials on the WKB approximation, and the rest depending upon your practice. So you practice different types of problem based on this. So there are the numerous the solved and unsolved problem in the quantum mechanics textbook, and especially you can look into the Griffith textbook of quantum mechanics, the quantum mechanics by Griffith, and the text one is your another one is your original textbook, which is by Zetley. So there are many problems available there. So just go through it and practice the problem. Okay, so thank you all, and next we will start the variation principle. Okay, thank you.